So, hello. I think it's time for me to start. My name is Viktor Kirilov, and today I'll be talking about interactive C++ compilation in C++, basically a REPL. So, about me, I used to work in the games and VFX industries, but for the past 3 years, I've only worked on open source, and my main focuses were compile times and runtime compilation. I'm also the author of doctest, which is the fastest C++ testing framework, and also the REPL I'll be presenting today here. Also, we don't have much time, so that's all about me. So, universally, C++ is behind other languages in terms of two things, in my opinion. One is package management, and the other is iteration times, which is comprised of compile times, and also the lack of a repo for interactive compilation. Have you ever seen this meme? It's actually present in all of my talks because that's like my sweet spot. So, a repo stands for Read-Eval-Print-Loop. And it's something like an interactive console where you can iteratively append and execute code, different statements, test things out, and also interact with an application. In this case, we're seeing the JavaScript console of the Chromium web browser. Inside of it, we can define functions, test things out, and even interact with the DOM of the HTML page. So, for C++, runtime compilation is usually done by replacing entire functions. So that's done either by using shared libraries or hot patching functions. It's been possible for decades, and it's usually quite intrusive, or you have to inherit from some interfaces, there are constraints, it's maybe hard to set up, but it's been done for many years, and there are many ways actually to go about it. The other way, when you don't want to replace entire functions, but to actually append code, like in a REPL mode, and you can actually mix global and function scope code. There's one project called Clink. It's developed at CERN, and it's built on top of LLVM. But actually, it's pretty hard to integrate in an application in a platform and compiler agnostic way. So I'll be presenting another technique to do interactive compilation in C++. Actually, all of these slides will be available later online, so you can just check out all the links. So why would we want runtime compilation for C++? Well, much faster iteration times. We don't have to restart the whole application. We can preserve the state and pick up where we left off. Also, there's no need for a scripting language, and so a lot of complexity just goes away. Also, we can hack something very quickly, like to do some queries, things which are not possible with a normal debugger. We can fine-tune values, and if we actually have interactive runtime compilation like a REPL, it's very useful for exploration and also teaching. So, the first demo I'm about to show we'll be using the following API. We have an object class with a few methods and 2 free functions to get all objects and add a new object. And all of this is exported through the interface of through dynamic interface. So let's continue with the first demo. Here we have some simple programming art scene with squares. And we can open up the console. And I have some preloaded snippets of code, which I'm about to compile. So first, we're including that header, and it compiled successfully. So the code went from this window to the window at the top where we have the already successfully compiled code. And here we have the compiler output. So let's add a new object. And here we see it in the middle of the screen, the gray spinning box. We can also change its color. We can interact with it with all the interface we have exported from the host application. We change its color. We can translate it, move it around. We can do anything. We can also slow all the objects in the scene, like a little matrix effect. And we can define new types. In this case, my type has a constructor and a destructor, which print some statements. And after that, we instantiate that class. Let's see what happens. We see here hello got printed, and if we're done with the session and we want all the variables to be destroyed and this history window to be cleared, we press the cleanup plugins, and we see that byte got printed here because the destructor got called. With this, we conclude our first demo. So, how does it all actually work? There are 3 section types: global, vars, and ones. Global sections are where code which has to live in global scope goes. That, for example, namespaces, function class definitions, and includes. var sections, that's a little bit special because that's where the global variables actually go. That's where our persistent state goes. And I'll go into much more detail in the next slides. One sections, that's where code which cannot live in global scope has to be. So it has to be in function scope. That's where we put our side effects and where we actually interact with the state of the program. So this entire snippet here, we can just copy paste it in our REPL and execute it. And as you can see, we've mixed different types of sections like global ones, vars ones. After that, we include the header, we define a function, and we call it. And actually, we're using comments to actually toggle between the different sections because that was the easiest way to implement it. So how does it actually work? When we submit code, we reconstruct the source file from all the sections submitted so far, at least the global ones and vars ones from previous code submissions. And we also use all the sections which we are submitting right now, including the once sections. We don't use the once sections from previous submissions because they're side effects which were already executed, so we don't need them. After that, we compile that source file as a shared library, and we link against the host application. If anything fails, we don't continue. After that, on success, we copy the resulting plugin with a new name, and we load it into the address space of the host application. We also don't unload the previous ones. And when we load the copy, that triggers the initialization of all the globals from the source file from a top to bottom way. And that is when actually all the once statements are executed and also the variables in the var sections are initialized. What we get in the file system is something like this, a series of different plugins which are constantly growing by a few kilobytes. And they're actually pretty small, and they're quite fast to build and link. After we're done with them, and we want to actually destroy all the objects we created, and we want to clean up the file system, when we do a cleanup, we actually call the destructors of all the variables from the var sections in reverse order, and we also unload the plugins in reverse order, which triggers the calling of the destructors of the variables which were written in global scope, and also we delete the plugins from the file system. So variables can be easily put in global and once sections as well, but when we put them in a global scope, they will actually be reinitialized on every resubmission of code. And if their initializer has side effects, they will accumulate. So that's what the var section was invented for, to have them initialized only once and to be persistent. Also, if we put them inside of a once section, they will be available only within itself because it will be actually put inside of a function. And also, in the demo, the compilation is done in a background process, so it's not a blocking operation. So when we submit code like this, a global section and the once section, we get the following source file constructed for compilation. First, there is the mandatory inclusion of a helper header file. Also, after that, everything from the global section is just copy-pasted in global scope. And whatever was in the once section is actually surrounded between the once begin and once end macros, which after the preprocessor get expanded to the following. A global dummy integer to which we assign the result of a lambda, which is immediately called when the plugin is actually loaded into the address space. So we use this integer to force some code to be executed in a top-to-bottom way within the source file when the entire plugin is loaded into the address space of the host application. We don't use that integer anywhere for anything except to get that cout to be printed. So if we have a few once sections, one after the other, they'll actually be executed in the same way, in the same order, when the plugin is loaded. When we define a variable in a var section and then we increment it, what we get after the preprocessor is something like this. We actually don't have an integer called a, we have a reference to an integer called a. And to it, we assign the result of the following lambda. Inside of it, we get the persistence for a variable called a. If we get the pointer which is not null, that means that that variable has already been created in a previous submission, and we just return the address, we dereference it, and we initialize the global reference. Otherwise, if this is the first time this variable is introduced, we're actually allocating a new integer using the same initializer. We're also registering the deleter for it so we can destroy the object when we're done with it. And we again return the address. So after that, when we're in the one section below it, when we're incrementing a, we are actually using a reference to an integer called a, not a itself. So there is some parsing going on for the var section, which I'll talk about later. When we have a variable using auto in a var section, here is what we do. So the bottom lambda is the same from the last slide, except that I'm not using the type itself, but I'm using a decal type of a call to a lambda just to deduce the type of the object that would have resulted from that initializer. So the lambda at the top is actually never used at runtime. It's only used to deduce the type of the object. So the bottom part is just like previously. We're making a reference called A, to which we assign the result of that thing. And we get the persistent pointer from the host application. So why we're linking to the host application? Well, most of all to interact with the application itself through the exported API. And also, because the source file always includes this helper little plugin, which has some helper macros. And it also has these two symbols which are exported from the host application for the persistence of the variables and registering their deleters. In CMake, if you want to actually link to an executable, you'll have to set this property in CMake to on. And about symbol visibility. Actually, Windows and Unix behave differently, but you could force one of them to behave like the other one and have either everything exported or nothing exported by default. And if nothing is exported by default, you'd have to explicitly say which symbols to be exported. And this is how it's done in a platform agnostic way. So here we have a bar function and a class. They're both annotated with my API. And depending on if DLL exports is defined or not, my API is either export or import. So the same header can be used when we're building the host application to export symbols, and also in the REPL to interact with the host application to import symbols and call them. So there are many health benefits to explicit symbol exporting compared to exporting everything by default, like better link times, maybe better runtime, also better load times, smaller binaries. If you want to read more about it, you should definitely check out the documentation in the GCC docs. But if you're going to be exporting symbols only for the sake of using this technique for having a repo, I would actually advise to not clutter your API, but instead just to export everything. So about the var section, you remember I said that we have to actually parse the type, the name, and the initializer from variables defined in a var section. So the parser supports complex constructs like templates, decal type, other initializers, references, auto, and only variable definitions are allowed inside of it. And it's also only 400 lines of code, so it's really tiny. Last night I attended this session by the CLIM folks, and it was so illuminating and depressing. So I'm pretty sure that parser is not good enough. So it's probably a bit broken and hacky, but guess what? It's only 400 lines of code. So there's some interesting restrictions to this entire technique. Mainly, if you define a variable in a var section, when you then do a decal type on it, you won't get the actual type, but you'll get a reference to the type because of how it's implemented. Also, you shouldn't be relying on addresses of functions, because when you define a function globally, and then you submit more code and you compile a new plugin, and it gets loaded again into the address space, actually that function lives again in the address space for a second time. So each time you submit more code, functions will be actually loaded again and again in the address space. Also, you shouldn't be using the static keyword because of the same reasons, because we load new plugins into the address space. Also, when in a var section we try to use a constant reference and we try to assign a temporary to it, it won't actually work and we'll get compile time error, because the way I'm supporting references with this technique is that I take the address of the object I get. So I cannot get the address of a temporary, so at least I get a compile time error and it doesn't just slide under the rug. Also, I hope you don't use the preprocessor inside of the code you're submitting. It could work in some cases, but I wouldn't do it if I were you. And also, just to reiterate this point because it's quite important, if you define global variables inside of a global section, they will be reinitialized on each recompilation, each time you submit more code. And side effects will accumulate. And that's what the var sections are for. So in my opinion, these are the biggest restrictions and notes you should keep in mind, and they're actually worth it. And for all the other small restrictions, you should check out the blog post. So Here is the entire API of the implementation of this technique. There are just 6 functions, like clean up plugins, submit more code, get new compiler output, or copy and load the currently compiled plugin. And here is how we would integrate it inside of the main loop of our applications. If we submit code and we're not compiling, we log the editor where we write code, we submit the code. After that, we continuously poll for any new compiler output to show it in the GUI. And if the compilation has ended, we check the status. If it's successful, we take the code from the editor and we append it to the history. We clear the editor, and we also copy and load the latest compiled plugin into the address space. So this is like so simple to integrate inside of a main loop of a program. The repository, well, it uses C++11. The whole technique is implemented in only 5 source files, which total to about 800 lines of code. And it uses one third-party dependency to fork processes, but that could be easily removed to make it blocking, or use your favorite library for forking processes. The rest of the demo repository is for the user interface. When you're integrating it in your applications, I would expect that you actually modify one of the 5 files, because it doesn't try to be a one-size-fits-all solution. So for example, the demo project uses CMake in order to work on all platforms and any compiler, so you can test it out. But that's not that optimal. You could call your build system directly, or perhaps Ninja, or even the compiler directly. Also, it would require a bit of knowledge about build systems, compiler, and linking, so you should know how to set up your project. Also, it's a good idea to avoid linking against big static libraries in the plugins themselves to make the iteration times faster. Also, it's a good idea to use a precompiled header for what you will be most commonly using. You could also disable optimizations for the plugin to make the build time faster if the runtime for the code you're writing is not that important, but you want to code in C++. And also, it's a very, very, very good idea to actually not have the editor where you write the code inside of the application. It could be some other real text editor, which with some plugin submits the code through sockets to the application, which compiles it and loads it. And that way, it will be much easier to support auto-completion and syntax highlighting, because without them, actually, development is impossible. So, where can we improve the whole technique? Well, the first thing on top of my head is to actually merge the global and var sections into a single one, because all we would like to know is which parts of the code we're submitting are global variables, and actually emit the special code to have them persistent. And also, if we go one step further, we could try to infer which parts of the code which was submitted cannot be in global scope and has to be in function scope. But I'm not sure how that could work. I mean, it's pretty complex. So in theory, it would be very nice if we removed entirely the need to have annotations through comments about which sections are, which code is in what section. Also, to reiterate, autocomplete and syntax highlighting are really, really important to have a REPL. Also, it would be nice if we have crash handling when we are loading the plugin. If anything goes wrong, to be able to recover from it in some way. And some other minor stuff. I also haven't thought about how to set breakpoints inside of the code we're submitting, or step through code. Haven't done that yet. So now I'm going to show a second bigger demo, which actually demonstrates why one would want to have a REPL, not just to test things out, but to have it integrated into their applications. So the demo uses the Dynamics library, which is about a new take on polymorphism in C++. It allows you to compose and modify polymorphic objects at runtime, and also it aids a lot in the complete separation between interface and implementation. So the way the demo is structured is that most of the functionality is actually split into separate modules, separate plugins, DLLs, and they're interacting with each other through exported interface, which is defined in the host application, the main executable. And also there is reflection, which is built on top of libclang, so all the classes in the demo have JSON serialization generated automatically for them. So the REPL in this case will be pretty fast because it uses a precompiled header, uses Ninja as the build system, and also it links just to a few static libraries. And also, almost anything is actually accessible, and you can change almost anything in the entire scene, in the engine, because it's sort of like an engine, the demo, because everything is exported and everything is split into DLLs. And also, almost all third-party dependencies are also built as shared libraries. Here's the precompiled header. Most of the standard includes, a few third parties, and some project-specific includes. So here on the left, we have all the plugins which are the different functionality, like editor, camera, mesh component, and also the plugin for the REPL. And on the right, we have the executable and the third-party dependencies. So all the plugins and the REPL plugin as well, they link only to the executable and to the third-party dependencies. They don't link to each other, but they can communicate to each other and interact with the objects by using the exported interface from the executable. And also, if we needed any functionality, like some free function which does something, we could write it in the executable and have it exported from there, so we can actually call it from either the plugins or the REPL plugin. Also, the whole thing supports a build mode where actually there are no plugins and everything is built into a single monolithic executable. So here goes the second demo. Again, it's not very much pretty. Again, boxes. But what can we do? Oh, I forgot to connect the mouse. So we can move things around. As we can see here, we have an undo and redo history on the bottom right corner, actually bottom left. So let's do some things. We did some things. What can we do as well? We can open up the console. And let's get all objects in the scene. Let's iterate over all objects and check which ones of them have a mesh component. And the ones that do, let's move them around. We can also get the world and get the camera object from the world and move it as well. We can also include the graphical user interface headers and the event headers. So here we're defining a frame begin event listener, which has an onEvent method, which will be called each time the new frame is starting in the game engine. And after that, we're instantiating that class to have a living instance. So here we see what we're drawing with that onEvent method on each frame, but we don't need it actually, so go away. Now we can actually serialize the entire state of our program to debug something. And here, what we're doing is we're iterating through all objects, calling serialization routines on them, and constructing a JSON file, which we then save on the file system. Now what? Now let's interact in a more complex way with the system. We're including the rendering headers. And here we're defining a new class, which then will register inside of the system as a mixin, which is something like a component which you can stitch inside of objects. And after that, we'll iterate through all objects in the scene. And each object, which has a mesh component, in this case the white boxes, we'll create a new object for them. We'll set it to be the child of the original white objects. And we'll attach this component to the new object, which has the green mesh inside of it. So here we see that above all of our objects, we now have green objects with the green component inside of them. And so we can actually do almost anything in the entire system as long as it's exported through the interface. Now let's close this demo and reopen it again. The scene is reset. There's nothing inside of it. You remember that I saved the state, right? So here I have a different snippet of code, which I'll paste. What it does is it loads the JSON file from the file system, and then it deserializes the state inside of the scene. Let's do that. And as we can see, it even deserialized the state of the editor. So I can actually undo in the history of the commands I previously made. So I can do absolutely anything with the entire system just because everything is so modular and exported through DLL interfaces. So this concludes the second demo. About it, well, if you're curious about the Dynamics library, Borisław Tanimirov gave a wonderful talk today about it on CppCon, which you should definitely check out. And also a little bit of bragging. Actually, all the separate plugins in this case, which are the editor, the camera, the mesh, they can be also hot swapped at runtime. And I can even change the memory layout of the classes which are defined inside of them at runtime. Because I have the best synergy between reflection and the interface and implementation separation thanks to the dynamics library. So yeah, that's pretty cool. The key takeaways about having a repo is that it's extremely powerful if your application allows for it. And also, the APIs should be dynamically exported to use this technique. Also, it can handle almost any C++ code or construct. And the demo project, it doesn't try to be a one-size-fits-all solution. You should hack it to fit your workflow. It also currently works on any platform and compiler. It's very tiny and easy to integrate, and it's full of comments to make it so you can easily understand it. Also, it will be a good idea to have a better parser for not needing the explicit annotations with the comments of the sections, and also to have a more robust parser for the vars type, for the globals. And yeah, syntax highlighting and autocomplete are crucial. Also, some random thoughts. This technique can actually be applied to any compiled language. I might soon do it for NIM. And suppose you're shipping a huge application. It might be cool to actually have an optional module for it, which is comprised of the REPL engine, the compiler used to build it, and perhaps your API headers with an export library. So you can ship that as well to some people who want it, who could actually, after that, play with your entire application if they have that optional module. And with that, I conclude the entire presentation. You can find the slides online, also the demo project on GitHub, and a bunch of alternatives to doing runtime compilation in C++, and some social media links. And now we have exactly 3 minutes for Q&A.
How difficult would this be to modify to make a JIT compiler sort of framework to execute maybe a list of commands provided at runtime?
Well, I'm not very sure. I haven't looked into things. Actually, the entire thing was inspired by my inability to get Clink working on Windows with Visual Studio. So I'm not much into running LLVM, and I haven't tried much on those topics. This was entirely born out of frustration of how complex it is actually to integrate something like this into a working program.
Okay.
So I haven't investigated that.
My question is about crashes and plugins. And am I right that this feature is only in plugin, right?
Can you repeat that?
I mean handling crashes in plugins.
Sorry, didn't get that.
Crashes in plugins. Does it?
Crashes,
Crashes, yeah.
Okay.
And am I right that currently it's not supported, right?
Yeah, but I don't think it's that hard to implement.
And I can't imagine how you're going to implement it if plugins are loaded into main process address space. It will crash a whole process anyway. It
I haven't investigated it in depth, but I know that Runtime compiled C++, which is another project which is doing runtime compilation in C++, it has some kind of fault tolerance. I haven't looked into it yet, but that was on the roadmap to check it out.
Okay, let's discuss it after.
Okay. Well, okay.
As far as I understood, you recompile your code, whole code to one library and unload old library and reload new library. Am I right?
I actually don't unload the old ones for some technical reasons. It could be done, but then some C++ wouldn't work. But when you unload all the plugins, you get all of them unloaded and deleted.
So the next version contains all versions of older like code?
Yes, without the one sections because they're already executed.
Why you don't break the input by like one library, one line of after enter dash?
Well, I haven't thought about that, but this was the most easy thing to implement. So, yeah. And session is over. Thank you very much.